All right, so we're here for Going Deep. We have the corporate vice president and some of his architects, and we're going to talk about the Vista kernel. So hello, can you introduce yourselves?
Yeah, I'm Rob Short, and I run the kernel and architecture team for Windows. The kernel team obviously is the core piece of the system, schedules, processes, we find devices, things like that. The architecture team is something that I wanted to talk a little bit about because about 2 years ago we realized that we were in a little bit more trouble in terms of our ability to predict the impact of changes and to make broad cross-group changes to Windows. And what we decided to do was have a core group of experts that would help the teams and work right across all of Windows to really help figure out the impact of changes and make sure that things were happening the way we'd like to see them happen. And I have some of the people with me here today. This is just a few of the people on that team. We have about 6 people full-time, and we have a much broader team of about 30 architects that work in the different groups. And they all participate as part of our architecture team, but they belong to the different teams.
Okay.
And the idea is to really improve our engineering process and improve our quality of our engineering and be able to predict the outcome of changes that we make.
Okay.
I've been in Windows for basically ever. I've been worked in Windows for about 15 years. I worked on a couple of other things in between. So I left and came back again, but mostly I've been working on where the hardware meets the software.
Excellent.
And I'd like to introduce my next partner in crime.
My name's Rich Neves. I've been working here almost 3 years. I work on the core architecture team, as Rob just described, and what my responsibility or role these days is figuring out how to police the dependencies between different pieces of the system so that we can figure out how to compose the system in a more efficient way. By efficient, I mean in a way that isolates developers from the damage they can do to other developers.
I see.
So basically, Microsoft's a very innovative company, and there's people working on amazing technologies in almost every nook and cranny, particularly in Windows. The challenge we face is delivering that innovation, and what our hope is that we can make innovation itself the bottleneck instead of delivering innovation, which has been the problem in the past. And to do that, what we're trying to do is isolate pieces of the system from each other, so that developers can know that they can work in a particular area of the system, innovating a technology, without adversely impacting larger parts of the system that, as Rob said, we can't predict are going to be impacted, and in a way that would actually jeopardize our agility in getting those features out that result from that innovation. So specifically what we've been doing is taking every binary in the system and assigning it a layer number, which is the rank in a directed acyclic graph. There's about 5,500 binaries in the system. And what we've been doing is getting transparency now into every dependency that developers add to any of those binaries, so that we can understand what's going on. And what's falling out of that is not necessarily just the isolation that I described, but also issues. We call them sort of conventional wisdom controversies. For example, people might be thinking, well, I want to combine a whole bunch of DLLs into one DLL for perf. Well, it turns out that that's a local optimization, not a global optimization. And it can adversely impact the global system. And we're catching that just by looking at dependencies and getting this isolation. So just to wrap up, my role is to sort of figure out how to police dependencies and model the entire system. And ultimately, we want to use that to get a whole in architecture too, and scale that out.
Fantastic.
So my name is Darryl Havens, and I'm on the core architecture team, working directly for Rob. And I was originally the I/O architect for Windows NT. I designed the I/O system and coded it, and like Rob, I left the Windows team, except that I actually retired for a whole bunch of years. And then he talked me into coming back. And for me, I think that some of us on the team play different roles depending on what day it is or something. One minute we're the glitch-free architect, 1 minute we're working on helping the Lua team or the low rights IE team, and the next minute we're thinking about what is it that we'd like to do to the system in the release after the release after the release after Vista. And in that particular case, my responsibility is to determine what the extensibility architecture for the system for the future is.
Excellent.
So I'm Rich Ward. I'm going to talk to him. I'm Rich Ward. Likewise, I work for Rob now. I spent 14 years in the security team. I did a lot of the security work for Windows all the way up until through XP, and then I came over to work on the core architecture stuff. And along with Darryl, I do a lot of incremental work, helping out other teams sort through specific problems. And then my broad-ranging problem for the release after the release after the release after the Vista is state separation. It won't be quite that far out in the future.
Fantastic. So can we talk a little bit about what's new in the Vista kernel? So when we go from XP, now we're going to Vista. So what are some of the new components?
A term I like to use is probably kind of politically incorrect on TV is some of the work we do is kind of like sewers. But if we do this work incredibly well, the stuff is essential, but nobody knows that it's there.
Yes.
So if things go bad, obviously you know about it.
Certainly.
Most of the work that I've been focused on for the last several years has been improving the experience where the hardware meets the software. Things like power management.
Okay.
We have a team of people looking at power management and working to improve how the system behaves. Say a laptop, for example, if you have a laptop, how fast does it turn on, turn off, how good is the battery life, what's the experience when you dock or undock? And we've done a huge amount of work on that. We've redesigned the algorithm for Hibernate so that we do a better job of figuring out which pages are already on the disk so you don't have to spend more of the pages back to the disk. We've changed the way the power management interfaces to the drivers so that we have a better feel for understanding if we can just shut this thing off right now. Today, in the older system in XP, we actually query the driver, say, hey, would you mind if we turn off the power? A lot of times people haven't coded up the driver correctly. Mostly the drivers don't care, whereas some really do. The disk driver, it really matters that you don't turn the power off in the middle of a transfer. But a lot of other things you don't care. Mouse, it doesn't really matter that much. You can go across the extreme. So we've done a bunch of work in that area. We obviously do a lot of work on performance. One example is we had problems with heap fragmentation, and we've redesigned some of the heap algorithms so we can deal much better with much more random requests, and we can deal with those and do a better job of defragmenting the heaps. So those are the types of things. Several people, Darryl worked specifically on the multimedia and understanding how we do a better job of not having glitches in multimedia, but that also goes right through the full length of the system. It's not just buried in the kernel. We've improved the inter-process procedure call.
Okay.
We have a new sort of fast, lightweight procedure call inside in the core parts of the system. Stop.
No problem.
He has a whole list.
I have a whole
Cheat list.
Well, there's a lot going on.
There's an awful lot going on. One area where we actually make a lot of changes over time that I feel really good looking back is in the memory management area. If you think about the early NT systems, Bill Gates used to beat us up and say, how come you don't run in 4 megabytes? And when you look at that today, and think we're running regularly in 4 gigabytes today, and we have systems in the lab that are running with a terabyte of memory, the algorithms that worked back then and the priorities back then are completely different than they are today.
Sure.
So we've put in work in Vista for improving the NUMA support, which is non-uniform memory access when you have a multiprocessor where some of the memory is closer to some processors than to others. So we do a better job of doing the allocation, making sure that you're allocating memory that's on the CPU, near the CPU that you're running on, and then we try and run the process on the CPU where the memory actually is, so you don't get cache thrashing.
Interesting.
We've done some stuff for the graphics. The graphics processors today are more powerful than the CPUs were a couple of years ago. So what we've done is done a better job of partnering the core memory management with the graphics processor, so we can actually keep windows in memory that are in memory not available to the graphics processor, and then we switch it over and give it to the graphics processor and say, we happen to know this is a window that belongs to you, and just flip it right over to that.
Nice.
So there are several of those kind of things. Another one that the people mostly on the server side would be delighted about is we've improved the way we do the virtual address space allocation within the kernel. It used to be we fixed allocated the address space in the kernel, and that leads to some problems if you have a machine that has a lot of one particular type of structure. Say someone is using up an awful lot of virtual address space. We ran out of page tables, and we fixed that, so it's completely automatic now in Vista. So those are just sort of some of the things. We've done some work to improve diagnosis. We've built what we call the hardware error architecture, so that if hardware devices fail, there's a way to get that information back in a sort of common way, back up to the higher level software, so that people can have a clue of what to do.
Sure.
You don't get a nice thing that says your device is dead, okay? We'd like to be able to turn that into something that says this particular device has a failure of this kind.
Excellent. Now, that's not necessarily error handling, right? I mean, you can still, if you have a device error inside the kernel, you're running kernel mode, you can still crash the system.
Absolutely. There's a big difference between actually detecting the error and being able to get it to the right piece of software, and then when you get to there, figuring out what you actually do with the error, whether it's recoverable or not, whether you can come up with a meaningful message. If we have failures in the kernel, we've made a policy decision that we don't actually know how bad it is, so we crash the system. And we try very, very hard not to do that.
Sure.
So that you don't actually, continue corrupting some information and keep running.
Absolutely.
But the idea is that for things that we understand the failure, we should be able to tell the user what happened. And a lot of that came out of the crash analysis data that we've done over the years.
Fantastic.
We've also built a framework. Speaking of drivers, we've also built a framework that allows us to run device drivers in user mode in a separate process. It's not inside the kernel, so it's not directly manipulating kernel data structures. It's not, it's not running in kernel mode in the first place. It's simply running in a user mode process. So you can, if something happens there, you can try and stop the user mode process and restart it, and your system comes. It's not that your system comes back; your device comes back, and it just comes back up, starts working again without having to bug check the system.
Fantastic. Similar to just like an application crashing.
Right, it's a very special application,
Certainly.
but yes, exactly right.
Okay.
Exactly.
So how does that work? I mean, so in other words, so if you move, say, an audio driver up into user mode, there obviously has to be some abstraction layers. So the way you're passing, it has to eventually get back into the kernel information.
Right.
So how does that work?
So basically, the device driver model before and today still for most device or lots of device drivers is that when a request comes from a user mode process into the I/O system translates that into what's called an I/O request packet, an ERP. And it fills in the I/O request packet with all the information that we need for what is it that this process is asking, where are its buffers, are they reading or writing, or what's the operation that they're attempting to do, et cetera, et cetera. And then what you would normally do is just pass that to the first device driver in the line of the stack of all the drivers that you want to get to that eventually get down to the device to go say, okay, here's what we're going to do. So what we do instead today is, in some of these cases, the I/O request packet comes into what's called a reflector, which then takes the I/O request packet from the I/O manager, packages up a bunch of data, and hands that off via an LPC, a very special LPC call, up to the user mode process, which then turns around and performs operations on its behalf.
Fantastic.
And then when it's done, it goes all the way back around.
So there isn't really a performance issue in that sense.
Well,
too extreme.
yeah, I mean, it depending on what kind of device you're going to use, it may or may not be, right? So the fact that this request, rather than being handed directly into from the I/O system to a set of device drivers, which could raise IRQL and lock out all scheduling in the system or dispatching of interrupts or anything, rather than doing that, when you hand that thing off to a user mode process, that user mode process, while it's special, is still a user mode process, and it has threads, and those threads have to be scheduled against all the other threads in the system. So if you don't set it up right, it's very possible for that thread to not get to execute for a really long time, in which case it's possible that you could have some performance problems. But you want to do this for something like a camera like this one.
Sure.
Right? You wouldn't want to do this for your paging device.
Okay. Excellent.
Or if you were sitting on a server, you wouldn't want to put the network driver in a user mode process and tell it to have at it.
Sure.
Wasn't that LPC mechanism you described one of the things on Rob's list? Was that new, that upcall mechanism?
It's not really an upcall, because basically what happens is when the user mode driver framework starts, it sets everything up and registers with the reflectors so that it knows what devices it's handling. Right. So.
Very good. So I heard you mention something about glitch-free media. What's multimedia? Can we talk about that a little bit?
Yeah, the problem we've got is there are so many things going on in NT, and NT really isn't a real-time, classic real-time operating system. And at the same time, you want to be able to take a piece of video and you want to stream it, so there's the problem of decoding the video itself, and then there's the problem of actually generating the pictures. And Darryl actually has worked mostly on this. It's across all of the different groups. It involves understanding the performance and time delays everywhere in the system, and then figuring out what are the constraints and requirements on each of the different processes that are running. I prefer Darryl to actually tackle that one.
You're on.
So basically the problem you get into anytime that you start doing anything where a number of applications in the system are trying to get a lot of system resources, and in some cases there are, even on really high-end machines today, there are video formats that it's not possible, if you had 100% of all the system resources, to actually decode the thing in time to hit the next frame. So basically what we've tried to do is we've tried to allow these kinds of applications to have as much system resources as they can possibly get, in particular CPU or memory or whatever, but also still have the system be responsive. So basically what we built was we built a scheduler that sits in the system. It's implemented as a service. And basically what it does is it schedules processes in the system, actually threads in the system, that have registered that say that I'm in this multimedia class and I'm busy doing one of these things and I'm in the foreground right now. Because you could have multiple windows and where one's laid on top of another one, you want the guy in the front to have as much resources as he can get, because if it glitches, it doesn't do you any good if the guy that's sitting behind isn't glitching, but the guy in front of you is just stopped. Right? So you need to understand who is it that's in front right now, and in some cases there may not even be a window associated with it if you're capturing camera or something like that in real time. So basically what we try and do is we try and take all the threads that are associated across multiple processes in the system, all the threads that are associated with taking this particular video along with its audio, and boost their priority to really high, like completely out of the normal scheduling range altogether. So basically today what's going on is these guys just keep fighting each other and fighting each other. Well, they don't have the privilege to get out of the normal range, so they're all sitting at 15. And they all think, I'm the highest guy there is. Well, what we did was we figured out a way of taking some of them, some of the time, and running them between like 16 to 23. But we don't let them run there forever. So what we allow the system to do is to provide a cell that's the system responsiveness, and that says these folks are allowed to use up to 100% of the CPU time and the resources of the system, unless somebody down here wants to use it, and then for some amount of time, 10% or 20% of the time, or whatever time you determine that you'd like to set it to, those guys get a chance to run. So we take all these guys that were running way boosted and put them underneath all the normal people, like your email program or your editor or something like that, and we just move them back and forth based on the amount of CPU time that they're getting. And so what that's allowed us to do is allowed us to give them huge amounts of resources, but not so much that your system becomes unresponsive. If you did this and didn't do it this way and let them have as much as they want, you probably wouldn't be able to move the mouse, but if you could move the mouse and then you clicked on something, the system would actually never see the click, right? You'd never be able to do anything like shut the window down. You just would never see that, right? So it would just use all the resources in the system. That's where people are moving, right?
Sure.
Because everybody's got the most important app there is, whether it's the game or the video or your email program, and you got to get that. I mean, you just got to go out to the net, and get the next piece of email. That's the most important thing in the universe, right?
Is this going to let people build new kinds of video games that run in a window? Because when I went to talk to the Flight Simulator group, they said, I want the whole thing.
Those guys are always going to want the whole thing because obviously the graphics looks way better at that. They can do it both ways, but anytime you get full screen, it's going to look way better. Whether you're the ultimate game or just playing a really nice high def DVD or whatever, right? So.
Fantastic. So Can we talk a little bit about where we're going, what the direction of NT is going? I mean, you talked about this at the PDC. We just talked about that a little more. Future of NT. Or the future of NT architecture. How's that?
Yeah, we sort of, the way we look at the world, at least in our group, we have a very biased world where we can get away with this and just be technology people. We're looking at the roadmap of the system for several releases and trying to figure out where would we like to be with the system, in 5 years, 10 years. And we try and imagine where we'd like to be. And then the releases along the way are just snapshots of that. Now the marketing guys would have a different thing where the release is the be all and end all.
Sure.
But what we want to be able to do is have this to be one of the most fun places for engineers to work. And obviously we have to have exciting, challenging engineering work.
Sure.
And what we've done is we've looked at the system from a few angles. One is most of the developers that you could be dealing with would understand this one. Richard at the end of the table is responsible for improving separation of state throughout the system. And over the years, the state in the system, which is anything from the user's files to settings to every piece of information that's scattered around the place, that stuff is not well structured in Windows. And it's grown organically. So if somebody wants to remember what their printer setting was, it gets stuffed off in some registry key somewhere. And now if you want to do a backup, the backup program has to know to find your registry key and back it up. So we made a list of the toughest problems. We put state right at the top of that list.
Okay.
To be able to really change the system the way we want to do it, we have to get control of that. And Richard can probably come in a little bit more detail than that. Then we picked the layering and componentization work that Rich mentioned a minute ago. And I think he sold himself short. There's some phenomenal technology in that I'd like him to talk about, the technology that we're using for that.
Excellent.
But really understanding the layering and componentization so that we can do engineering in parallel and that we can build pieces and really predict the outcome of the changes. That's very important. The application model in Windows is pretty complicated. Putting it politely, we don't really know what the app model is. Lots of apps are slightly different. We're not quite sure where an app is supposed to put all its information. There are some guidelines that are out there. Not everybody follows the guidelines. So we'd like some better guidelines on application models so that if someone wrote an application, we could predict if the next version of Windows is going to break that.
Okay.
Another area that's fascinating is extensibility. Our whole world exists because of extensibility. And extensibility means somebody takes a piece of code that they write and put it into Windows and it changes the behavior of Windows. So a device driver falls into that category, a browser helper object, shell extensions, everything in between. And Darryl owns figuring out what the future of those things should be. For example, we'd like to be able to know what they are before we load them, so make sure they're not some spyware or some malware or whatever. We'd like to have an idea where it came from. We'd like to be able to load it in the system. We'd like to make sure that if it fails, the system is resilient to that failure. You'd like to be able to inventory them so you can look at your system and figure out why it's crawled to a halt.
Yes.
Right, so
absolutely.
you have to really understanding all the extensions in the system is incredibly important. So we've got Darryl working on that.
Excellent.
The other thing, of course, is compatibility. And there's a term that our chief software architect uses that he says if you break compatibility, you're throwing away an asset. At the same time, when we change the system, we don't know if we're breaking compatibility sometimes. So we're looking at several different ways using techniques such as virtualization to figure out if we can actually really guarantee that one version of Windows can always run the older applications. So those are the things that we're looking at from an architecture point of view going forward. There's some of the things.
Excellent. Very, very cool. All right. Well, let's hear about layering. You're on.
So the most important thing that we're trying to achieve is isolated engineering, as I said before. And Rob wanted me to talk a little bit about some of the technologies we're bringing to bear on that. And one of those technologies is something that Microsoft's has had in its back pocket for, I don't know, several years now, which is technology from research that allows us to analyze binaries and understand their dependencies.
Okay.
So this means, this is very significant because it means that we can look at compiled engineered code, the binary, and determine what are the functional and then of course binary dependencies on other binaries, even if it's dynamic dependencies. So for example, we can look at a binary and the tools that we have allow us to do data flow analysis and actually watch the values of variables in the code, not as it's executing, but analyze it statically and find that, oh, this has a COM dependency on this other GUID over here, or class ID, or we have a load library dependency on this function name in this binary. So we can find what nobody thought that we could be able to find before pretty accurately. I think Craig Shirt's the owner of some of these tools, would get mad if I claimed a percentage, but we're approaching asymptotically the best that you could possibly do with this. So given that as a basis, we now have, the tens or 100,000 or so, I don't actually know how many it is, probably not in 6 digits, functional dependencies between binaries. And we have this wealth of information to look at. And we looked at it very, very carefully about 2 or 3 years ago. And our interest in this data was to understand how can we tease apart pieces of the system from the other pieces of the system to limit impact. So just concretely, what if we wanted to, with 100% confidence, modify the shell in the higher layers of the system without worrying about retesting or rebuilding or re-architecting the lower layers of the system? Now, conventional wisdom would dictate that should be a problem. Well, it turns out that of those 5,500 binaries I mentioned, using this information in these tools, about 300 or 400 binaries are in what we call a strongly connected component, or more affectionately known as the big cycle. These binaries are all IE and shell binaries, and they were produced at a time, these dependencies between them were produced at a time where we didn't have any sort of discipline around taking dependencies. And this leaves us in a situation where if you modify a higher level part of the system, you may well impact lots and lots of binaries underneath without even knowing it. And this limits our ability to not have to test or engineer or architect or any verb you come up with for engineering the entire system, which is very costly for us to engineer the entire system. Sure. So what we think of today as Windows, we actually, from a dependency perspective, see as a single big binary. And now you asked about the future roadmap of Windows, and what we're aggressively pursuing here is splitting Windows into at least 2 pieces in the first round, and n pieces in the longer term, where we have almost a firewall between the bottom and the top parts of the system, so that we have completely 2 separate engineering processes, 2 separate build trees, and we're able to actually build internal release engineering timelines that will allow us to get out of this lockstep engineering where everybody's building their new features on the assumption that other new features will exist. So this is a really exciting reality if we can get to it, because we'll be able to get out releases very, very, very quickly. We'll have teams pipeline developing new technologies in Windows very, very quickly. And this is important because Microsoft's had traditionally very independent engineering teams in terms of what they decide to work on, and that we'd like to keep as much as that as we possibly can because it garners innovation. But we want to just federate a little bit of that and understand how if you could just follow these sort of guidelines and not take these dependencies, we'll be able to let you go out and knock yourselves out doing some really great technology.
Fantastic.
So what we have now is an automated build process and a peer review and architecture process where if somebody takes a dependency that violates some of these axioms that we have, they come in and talk about it. We solved a lot of problems already that way. Our mantra so far has been to keep the system from getting worse in Vista in terms of dependencies. But at the same time, we've developed this map. We have like a 10-foot tall map, a graph actually of all the binaries in one of the halls down here in Building 26. And that what we've done in the process of not keeping things from getting worse is we've mapped out the entire system. And now we can look at it and say, we're going to partition it right here. And we're going to go ahead and have this be a separate NT tree and this be a separate NT tree. And the key thing here is that this isn't just about engineering isolation from a writing code perspective. It's also about architecture, because now you can think about saying, okay, Joe Smith, we're going to have you be the architect for the networking stack, not the IPsec stuff, just this network. The TCP IP stack goes down to NDIS, and maybe some of the helper DLLs on top, and you're the architect for that. So now we can actually isolate architecture, and we can get some best practices that we define by the domain experts in those areas, and we can delegate to them and say, keep those best practices in line. And now, instead of having this very large system where we don't understand where the change is happening and the impact of that change, now we can go and delegate to architects across the company who actually now can, with confidence, say, I architect this piece of the system, and I know that if bad decisions are made in here, they're only made in here, and I also know that I'm protected from the bad decisions made over here. And so we can catch things that are bad when they happen sooner, and get Windows towards a place where we are very agile and very quick to get new features out to customers.
That's absolutely amazing. And also be more stable, more reliable,
Yeah.
right? Fantastic.
God, Rich, you did such a good job. It makes me want to come work on it. That's great.
It makes it sound so easy.
Yeah, exactly.
We'll probably wrap up with that, right?
What you just said is probably 4 years worth of work, right?
You've been very quiet.
Yeah, what's going on down there?
You could talk about state, you could talk about what we had to do with the system to make the protected admin work.
I don't know if we want to air all the dirty laundry necessarily. I thought we were going to look for the future.
Oh, yes, we did.
Actually, well, I was actually kind of hoping that Darryl would go for me, because the state actually serves as a good wrap-up to see how everything kind of ties together. Because, as Rob alluded to, we've got a lot of goo in the system, both for applications, because applications spray their settings and their state and their installation options and all the other stuff all over the place, and the system is even worse. And as much as we like to point at the apps and say, oh, God, if only Office didn't do that, we'd be better off. The reality is that it's the network stack and the Windows stack and the shell and all these other areas that also exhibit all these problems and spread their idea of what things should be like everywhere, and it's hard to predict. And it's hard to predict where things end up, and it's even harder to gather them all up again and move them someplace else, for example. So what's very cool about the state stuff is that it separates into different areas like application state and system state and user state and preferences. And we've made some inroads there in terms of letting users' configurations and choices migrate with them wherever they go. But the system itself is still kind of a big binary, as Rich likes to point out. And so I look at when Rich is getting very excited about his layering work, I say that yes, it's very cool, because as every area in Windows gets isolated in the layering plan and area architects get assigned, I also know that we're going to capture and isolate the state for that particular area as well. Because there's no way that you could have the engineering done in isolation of the rest of the configuration. So the layering map says that, oh, okay, yeah, there's an engineering value. People will gain the perspective on their own systems and components. As they do that, they'll naturally be moving towards a more state-separated model, where they're going to have to capture what they want to do and carry it around with them, because otherwise they won't be so isolated. And so I've got that as a leverage point. And so my real task is to come up with a plan for how they're going to represent all their state settings and how they are going to be captured and contained and moved around. And we've got some minor ideas, and we've got some projects going on about how we can change the way the registry works and do some interesting composite views, and how we can leverage the class storage in the COM world that's already being done right now for click once. How can we make that more prevalent? How can we use it? But that's comparatively minor when you look at, okay, let's take the whole system, split it into chunks that can be assembled in meaningful ways, and then with every chunk of code, there's actually a chunk of state.
Fantastic.
Configuration.
So but this doesn't necessarily remove dependencies. It makes it more understood what they are. I mean, is that fair to say? So in other words, it sounds like, because on the one hand, it's componentizing the operating system. Or
Well, what I was talking about were functional dependencies between pieces of the system, and what Rich Ward's talking about are state that's not necessarily aligned with how we partition up the system. So if two different binaries share a registry setting, but they're at two completely different layers of the system, we've gotten a lot of isolation from a functional dependency perspective, but we still have this problem of unintended consequences in modifying that shared registry setting when it's shared by these two pieces, and that leads to all sorts of problems with trying to migrate people between machines and trying to just build systems that don't have some of those binaries sitting around. It's a real problem for us.
Do you guys wish the registry had never been developed?
The registry,
Should ask Richard.
Oh, it's especially ironic for me, because I remember going to one of the Usenix conferences and extolling the virtues of the registry as opposed to those old text files. Who could possibly use those things? It's not quite eating your words. The registry performs an important function, and it's a victim of its own success, right? If it stayed what it was originally, which was basically a place with moderate structure that the system was allowed to store its GUI in, and that was it, we wouldn't be that bad off. But it grew, as we like to point out, organically. It's much easier to dump your settings here, or if I need to remember something from one build to another, or one boot to another, yeah, look, here it is, it's in this key in the registry. And we didn't want it to be a general purpose database, and maybe we should have in the past. That's one particular path. But if it was a general purpose database, then it would be, it would be more tangled and bizarre. Can you imagine saying, okay, I'm going to project the results of a certain merge across all the following different settings to decide what I'm going to do? I don't think we need that either. I mean, some level of predictability.
Sure.
So I don't regret yeah, I'll see you edited that one out, buddy. I don't regret the registry being developed.
Sure.
It's unfortunate the registry was overused.
Now wait a minute.
Actually,
There are
overused is the wrong word. Sorry to interrupt.
no, not at all.
I actually think
It's how it's used.
overused is the wrong word with the registry. The real problem with the registry is we never actually defined the set of guidelines and schema for how people should use it. And if we had done that, we wouldn't be in this mess today.
Understood.
So how are you guys going to get us out of the mess?
That's what Rich is doing.
Yeah, we're going to get out of this mess. We're going to plow through it. And the big debate is how much of it can be done in a compatible way, and how much of it we're going to count on the application compatibility work that Rob was mentioning to save our skins, as it were. As I mentioned, we're doing some prototype work with compositive views of registry keys. Yeah, it's actually pretty cool. We can do that in a very compatible way. We can do it in a way that provides value to the actual ISVs to adopt slightly different semantics and how they read from the registry and make use of the registry. Kind of force them into the schema that we would like them to use. Is that, it's not free, but it's something that can be done with comparatively low impact to the application and make them want to adopt that methodology. You could also come up with a new scheme which said, hey, let's do it with this database where everything is a structured query. Like, yeah, you can do that, but boy, would that be painful for anyone to transition. And Rob likes to talk about application compatibility. It's something very important not to give up. I also refer to developer compatibility, right? Because if you come up with a completely different methodology for doing something, then it's difficult for the developers, the developer community, to adapt to it. And we're kind of nailing that right now. Right? We've invested a lot of money in moving to the new .NET Frameworks world and have the new programming model and paradigms that brings. Doing yet another one, and yet another one, yet another one, is only going to churn the community. And so we need to do things in a way that lets people apply the knowledge of the game from a new platform or framework or methodology across a broader swath of our own platforms.
No, no. Always.
I was going to say that one of the things that's
What, we can iterate each other?
Your threads are always at a much higher state.
Right. So, I mean, another way of answering that question is, one of the things that's really important in answering that question is, I kind of tongue-in-cheek stated that we were working on things that were the release after the release after the release. Basically what I'm trying to say by that is, eventually someday we want to be here. We need to define now where it is we'd like to eventually get. And then what you do is you go back and you ask, what can we do in the next release to get us toward that? And those are the kinds of things that Richard's talking about.
Fantastic.
So, I mean, one of the things that Rich Neves didn't say was, once you've drawn that line, other than you take the box on the top and draw another line and iteratively keep doing that and doing that and doing that until you've got these people over here. We have an entire team. There are 300 people working on this one thing, but they don't affect anybody else, right?
Yeah.
They can change forever and ever and ever, and you'll know that you never have to rebuild the rest of the system. You know it doesn't impact anybody underneath them or anything else, right? And that's part of what he was saying, but it's this iterative process, right? We're trying to do that for state. We're trying to do it for application models. So.
Now, what about for like memory and the problems caused by shared memory and the problems that are even going to be even more serious as we get into the future of hardware and stuff like that? So is there work going on in that area?
Or to take it into a different... to take it into a different world, I talked with
ask that question.
Matt Mullenweg last week, who runs WordPress.com, and he said he's having a huge amount of pain because he's having to build data centers around the world where he's going to have a huge number of users using his boxes, and he wondered how is the OS going to change in the future to help him build data centers out, like a grid kind of style. He says, I want a Windows computer that I just plug into my data center and it federates, and I don't have to do any work. Right now I have to do all this work. So are you guys thinking about that kind of usage model and how that will change Windows?
We haven't been working on the management per se. There's a whole team of people working on how do you actually manage those. From the grid point of view, from the scientific grid, we actually announced and demoed a product called Compute Cluster at the Supercomputer Conference last week, right here in Seattle. And that's exactly that, but they're focused very much in the near term on how do you take computing jobs that are very related and controlled. But you should at least look at that. The management tools division is looking at a number of different problems, particularly how do you take a large number of machines and manage them as a single entity, and particularly manage them from the point of view of the thing you're trying to do with them rather than the fact that it's a piece of hardware. You want to see your database. You don't want to see 12 computers. So how do you be able to need to see, how do you see 12 computers when you need to see them and see your database across the whole lot of them? And then get the database be more powerful. And we have a whole division working on that. That's outside of our area, really.
Yeah.
And this stuff is going to hit
core.
all of our business. I mean, we're talking about services, and some of my friends are putting services now on thousands of computers across the world and having data centers, across the world federate. Like my blog right now is running on, you don't know how many machines it's running on. When you hit my scobalizer.com, it could be coming from up to 4,000 machines is the way he architected it, but you don't know where they're coming from. And it has a common experience, right?
Right, and when it
like you
goes
said,
bad, figuring out what happened is another
Yeah.
interesting thing. So you need enough information so you can understand where the information is, what state the thing needs to be in. And Anders Winberg, who's the architect for the management tools, who's probably worth talking to,
Sure.
uses one term. He says oughtness, meaning what state do you think the thing should be in, and then he has the other term, which is isness. Right, and then you have to figure out what the difference between those two states is across all your thousands of machines.
Sure.
And they're working on that. You should talk to them about that.
Absolutely.
The shared memory question I didn't quite understand.
Well, I was just, we were talking about the roadmap
Mhm.
of Windows, and you had mentioned, layering and understanding dependencies,
Right.
functional dependencies, and then state, and then work being done in the I/O world, taking drivers out of kernel mode, making it more stable, reliable, etc. But one of the core problems in an operating system where depends on where there's shared memory is the ability to hang.
Oh, you can trample someone else's address
The
space.
ability. So is there any sort of future thinking in terms of like isolated
Yes.
memory?
And there are we have several different projects going on in that area. Darryl mentioned, for example, the user mode driver framework, which is taking a driver and instead of having the driver run in the same address space as everything else in the kernel, it takes the driver and runs most of the code in the driver in the user space
Sure.
and then comes back down into kernel when it needs to. That's one big one. We have a virtualization product, virtual PC and virtual server that we sell today. Those live in their own isolated spaces. And we're looking at ways inside the system to see if we can actually isolate some of the processes that are running completely in their own address space. And that's something that we're just looking at as more an advanced development thing. The design decisions, Dave Cutler would disagree with me on this one. Hey, Dave. The design decisions that we made in NT at the time were probably the right decisions given the performance of the machines and the amount of memory available. The machines today are at least 1,000 times faster. The memory is anywhere from 1,000 to 1,000,000 times bigger. So I think it's possible to do something where you could have more address spaces.
Sure.
And isolate the drivers in different, come up with a much more isolated model, more like the sort of traditional microkernel. We are looking at some of those ideas. We're not actively going full speed ahead on them today.
Excellent. And then also, we're going kind of way further out into the future. Is NT going to get, say, smaller over time, in the sense that? So when we think about Windows in general, do you have? Where you, I mean, because so basically you have the one big mama kernel or medium-sized kernel, and then you have everything else around it. But are there thoughts about architectures where you'd have a smaller mama kernel and then maybe satellite kernels, like virtual machines?
We've spent a lot of time trying to figure out how do you get one code base that goes from the telephone all the way to the huge device, right, to the data center or whatever. And the funny thing about that, if you look at the continuum of machines, the data center actually isn't the complicated one. The client that does multimedia and does all the web browsing, that's the one with all the complexity in it. The data center one is actually more simple and more bounded than that. But today, we really don't have a way to take the pieces of the system and mix and match them. And one of the pieces that we've been looking at from the componentization is trying to define what we consider the minimal system, and what would the minimal system be built out of, and what are the requirements for that. For one thing, for example, we thought about surely you'd need a system that's a tiny little system. It doesn't have a networking stack. It doesn't have graphics, right? It's a little tiny thing. And then we couldn't actually imagine a system that didn't have a network anymore. Your phone has a network. Your gas pump, which runs NT, has a network.
True.
Right? Everything has a network these days. So we've been looking at that, but because of the pressures of particularly the desktop space, it's been hard to get enough energy on it and get it done.
There's a back pressure on that too. I mean, if we try and componentize and layer the system, and we get to this, as Darryl was describing, you know, we componentize more and more and more and more, and we end up with 2 and then 4 and then 8 and 16 and 32 partitions. You take that to a point, and all of a sudden you start really looking at the bottommost partition and saying, what are the contracts that it's exporting? Does it really need to export these? Because I really want to engineer just pieces of the kernel in isolation from other pieces of the kernel. So there is it's sort of implied by the direction that we're going with partitioning that we do take a look and re-examine the one-size-fits-all philosophy for some of the pieces of the system at the bottom. I mean, we already see in NTFS and NTOS and NTDLL and kernel 32, these are very basic binaries in our system, that they're growing faster than we are comfortable with as architects because of the pressures that we have from applications up top that are asking for features to be enabled in these bottommost pieces. And if you look at these things that are growing, and you look at why they're growing, the question is easy to ask. Why didn't we make transactional support separate, maybe? I'm not a file system expert, so if the file system guys are watching, please don't beat me up too bad. But this is a big feature that we added to the file system.
Absolutely.
That'd be interesting to ask, can we modularize that? And the benefits of doing it aren't just for elegance or anything like that. It's, again, for engineering isolation. And if we're going to have a system that could be built as an embedded device, should that embedded device necessarily have transacted registry, transacted file system support? Should it have code integrity in the kernel for obfuscating code? You know, I mean, there's a bunch of things that we have. This is a big operating system. It serves lots and lots of different purposes. And we're beginning to get to the point where if we just throw all of those different requirements into one thing, we're beginning to see how that can hurt us. And of course, we've already seen how it can hurt us in user mode with the big cycle and the 5,500 binaries that are all tied together with 300 or 400 in a big cycle together. But there's an analog down low in the kernel, I think, that we're going to be asking these questions about specialization and not one size fits all. We're going to be asking those over time. I don't know if these guys agree with that.
Well, that's fine. I disagree. Nothing better than watching architects argue.
Yes, there is.
All right, in this context.
Okay.
Fantastic. Well, you know, do you have anything else you'd like to say? I mean,
Actually, one very important.
Please.
I forgot one very important point. The work that we talk about here is being done by lots of different people all across the division. We're not doing all the work. We're catalysts helping the work get along, and I want to make sure that everybody, you know, understands that there are dozens of very, very good engineers doing all this work. It's not just 4 of us sitting here pontificating and telling them how to get it done.
sure. Of course.
Looks like we have people waiting for the next meeting.
Hey,
right
well,
out
thank
there,
you guys
so
for your time.
Thank you very much.
Really appreciate it.
Awesome.